A homogeneous linear recurrence relation, where all the AI's are constant, has general solution based on the roots of the characteristic equation. But we can make it non-homogeneous by adding a forcing function, a function of n and not the other terms of the sequence. For example, this is linear because it's a linear combination of the terms, homogeneous since the only terms are those of the sequence, and second order since the two preceding terms are required. But if we add a function of n, say 2n plus 5, then it is a non-homogeneous, but still second-order linear recurrence relation. At this point, an obligatory joke. How many mathematicians does it take to screw in a light bulb? Just one. They give it to 3 plumbers, thereby reducing it to the previous joke. This joke explains a few things. First, why HBO isn't returning my calls, and second, how mathematicians approach problems. Since we know how to solve a homogeneous relation, can we reduce a non-homogeneous relation to a homogeneous one? So to avoid learning how to think about mathematics, you can look up the answer. But if you can do that, so can someone else making half your salary. So let's try to create a solution. Remember, don't learn to solve problems. Learn to create solutions. So concrete doesn't hurt, so let's start with the simplest case, which would be an added constant. Now, if I want to make this homogeneous, what I'd have to do is somehow get rid of that plus 5. So I'd need to subtract 5 somewhere along the way. And the insight that's useful here is that all terms of our sequence have a plus 5. So if I take a look at, say, the term before Sn minus 1, it will be, and now I can subtract, and get a homogeneous second-order linear difference equation. Let's see how that might work. Let's take our recurrence relation where S1 is 3. So we've rewritten this as, since this is homogeneous, we could write down the characteristic polynomial and find its solutions. So x equals 1 and 2, and so our general solution will be since S1 equals 3, we have, now we have 2 unknowns, C1 and C2, so we need another value of Sn. But we're only given S1. How could we possibly find another value? Well, we do actually have the recurrence relation. So we can use our original recurrence relation to find, and that gives us S2. Substituting the values of S1 and S2 into our recurrence relation gives us, and solving gives us, now that's what happens if we add an added constant. What if we had an extra linear term? So let's think about that. So as before, we have our linear recurrence relation. We look at a previous term, how about Sn minus 1, which will be, and now if we subtract, we get, which is not homogeneous. But wait, we just solved the problem where we had an added constant. We'll just subtract the previous term and get, which is homogeneous. So we might try to find a closed form solution for this. We could rewrite it as our characteristic equation has roots 1, multiplicity 2, and 2. So our general solution is, and since there are 3 constants, we'll need 3 initial conditions. And so we find And our initial conditions give us a system with solutions